The rather long example we used for a system in the previous lecture, the power cycle or heat engine, serves to go back to another version of the second law of thermodynamics, which states that it's impossible for a device to operate and produce a net amount of work if it only receives heat from a single thermal reservoir, without dumping heat into a low temperature reservoir. This is what is known as the Kelvin-Plank Statement. We know that the second law helps us restrict the conservation of energy by giving it directionality. We know that heat spontaneously moves from a high temperature to a lower temperature. But just like it is possible to turn heat into work with a more complex cycle like the power cycle or heat engine, the only way to transfer heat from low temperature to high temperature locations is via a refrigeration or heat pump cycle. These cycles operate in a very similar manner to the power cycles or heat engines. We talk about refrigeration or heat pump cycles together because they basically work in the same way to each other. The only difference is that in an air conditioning system or refrigeration cycle, we want to keep a volume cool, while heat pumps are usually used to keep a volume warm. The system schematic for this refrigeration/heat pump is very simple. We have a low temperature reservoir from which we are going to extract heat, and we are going to provide heat to a high temperature reservoir. Of course, we can only do this if we provide the system with a net work in. Otherwise, this would not be possible. These systems consist of an evaporator, which is similar to the boiler. We just call it evaporator because as opposed to the boiler where the temperatures are really high, evaporators work at normal temperatures, but they both turn liquid into vapor. Then we pass through a compressor to obtain a high pressure vapor, which requires work to operate, and then the fluid passes through a condenser, and then to a throttling device/expansion valve. Just like in the power cycle, both in the evaporator and condenser, the pressure remains mostly the same and any changes are negligible. The evaporator is where we take heat in from a low temperature source, and notice that we should be saying source as opposed to reservoir, as depending on if it's a heat pump or a refrigeration cycle, we do want for one of these sources to change temperature as it loses or gains heat. It's not an infinite reservoir that remains at the same temperature despite the heat that we add or remove. So we'll still say reservoir, but just know that the low and high temperature locations can still vary in temperature if heat increases or decreases. The compressor, which was initially described as the opposite of a turbine in the steady state mechanical devices lecture, link below, brings up the pressure and temperature of the fluid while using work, as opposed to letting the fluid lose pressure and temperature while producing work, which is what happens in a turbine. This means that the constant pressure in the evaporator is low while the constant pressure in the condenser is high. Same with the temperatures. At the condenser, heat is rejected into a high temperature reservoir. Now it sounds weird to say that we take heat from a low temperature source and provide heat into a high temperature reservoir or warm reservoir. But this is not contradicting any thermodynamics laws because, like you see here, the temperature of the fluid at the condenser is already high, even higher than that of the quote-unquote high temperature source. So heat will spontaneously flow from the high temperature of the fluid to the still relatively high but also lower temperature of the warm reservoir. And the opposite is true for the evaporator, since the temperature of the fluid is low, lower than the temperature of the low temperature reservoir or cool reservoir. And finally, from the same lecture linked below, we remember that the throttling device will maintain the enthalpy of the fluid while also dropping its pressure considerably. So let's position this cycle schematic inside each of the three most common examples for refrigeration/heat pump cycles, beginning with an actual refrigerator or fridge. In a fridge, the interior volume where we keep all the food and items we want to refrigerate would be the cool reservoir. We are removing heat from it into our fluid, in this case a refrigerant, not water, which is even colder than the refrigerated space, and we want that refrigerant fluid to go through the rest of the cycle. Our warm reservoir would be the surrounding volume outside the fridge, usually the back or the bottom of the fridge. A freezer would operate on the exact same type of cycle. In the case of an air conditioner, the cool reservoir would be the space that is being cooled, for example a house or a car, and the warm reservoir is the exterior, which if you're running the AC at all, is most likely already hot. We take heat out of the cool space to toss it back to the warm exterior. And finally, we have heat pumps, which are used to bring up the temperature of a space. These are of course used to make spaces warmer, and they are usually used in places that do not get that cold. These types of heat pumps are common in coldish weather locations, but not extremely cold regions of the world. If you're interested in what is used in colder places, I'll leave a link to that in the description of this video. What's cool about these heat pumps is that it's the exact same unit as your air conditioning system. They just operate in the opposite direction to the refrigeration cycle. When you set your house thermostat or a car's AC to heating instead of cooling, all we're doing is changing the direction of this cycle. The cool reservoir is now called warm, a warm car or a warm home. The warm reservoir is now called cold, the cold exterior, and the condenser and evaporator just changed names. These two are really just heat exchangers. Remember that steady-state mechanical device we covered in the third of the 3 series lectures? It's linked in the description below if you need a refresher. So they'll basically allow the exchange of heat between the refrigerant fluid and the surrounding air. Of course, a fridge, an AC, or a heat pump doesn't just allow the heat transfer to occur through natural convection, meaning no forced airflow. There is always some sort of fan that forces the air to flow at a certain speed, like in a car's AC vents, so that the heat transfer happens at a quicker rate through what we called forced convection. You'll learn more about those types of heat transfer in your heat transfer class. Link to that course's playlist down in the description of this video if you're interested or plan on taking that in the near future. Now, in cycles like these, we don't talk about efficiency, since under the definition of efficiency, we would be getting values greater than 1. In these types of cycles where we're adding work so that the cycle happens, we call it coefficients of performance to assess how well the refrigeration or heat pump cycle performs. You can still think about the term as how efficient these cycles are, but just not from the thermodynamic meaning of the word efficiency, just how well they perform at a task they are created for. The coefficient of performance, or COP, is therefore dependent on the goal of our system. In general, the coefficient of performance is defined as the desired output over the required input. But for example, for a refrigeration cycle, what we want is to get heat out of a cool space, so the desired output is Q in and the required input is W in. Notice that it's heat out of the cool space, but that heat is coming in to the fluid of our cycle. And just like we did for the power cycle in the previous lecture, link below, drawing a control volume around the entire cycle, from our energy conservation we see that W net is equal to Q net, or Q in minus Q out. And since the net work is the only work which is coming into the control volume at the compressor, and work coming in is by convention negative, W net is minus W in, and therefore work in is Q out minus Q in. And this is applicable for total energies W and Q's, or energy rates W dot and Q dot. This means that it's applicable with heat and work, or heat rates and power. In the case of heat pumps, the desired goal is to heat our house, or any space, and therefore the desired output is Q out. For that reason, the coefficient of performance becomes Q out over W in. Everything we learned here agrees with the second version of the second law of thermodynamics, also known as the Clausius Statement, which states that it is impossible to construct a device that operates on a cycle and produces no effect other than the transfer of heat from a low temperature body to a high temperature body. Let's look at a really simple and quick example on coefficient of performance, and if you want to check out other examples on heat pumps and refrigeration cycles, make sure to check out the links in the description below. What is the COP of a heat pump that supplies heat to a house at a rate of 6,000 kilojoules per hour for each kilowatt of electric power it draws? What is the rate of energy absorption from the outdoor air? From what we learned today, the COP is the desired output, meaning the heat that we're providing the house with, and again out of the device into the house, over the energy or work that is being drawn. We substitute the values, we do a simple unit conversion, and we find a COP of 1.6 repeating. As for the heat rate being absorbed from the surroundings and from a simple control volume, we know that the heat we took plus the energy we added is the heat provided to the house. Therefore, the heat in is equal to the heat out minus the work. We substitute the values, again with a simple unit conversion, and find that the heat in is 2400 kilojoules per hour. And that's it. Like I said, if you want to check out other examples on this topic or other lectures of the thermal course and other engineering courses, make sure to check out the links I left in the description of this video. Thanks for watching.